Good morning, everybody, and hello to our third weather briefing in this year. Some of you probably already know me. My name is Liliane Hofer, and I'm working at the Central Institute for Meteorology and Geodynamics in Austria, but not in the headquarters in Vienna, not here, but at a regional center here in Salzburg. So as you see, we have an empty European map here, so please take a star or take this star, for example, and mark where you are from. So I can get an overview whom I'm talking to. Okay. So I see many people from the Eastern European countries. Okay. Thank you. And today it's a special weather briefing because we have some guests from Indonesia as well. After my talk, my colleague Anna Setiawati will tell us something about the weather conditions in Indonesia. And for our guest from Indonesia, I have here a map, and so please put your stars from where you're from. Okay, so I think that's it. Okay, now we start with the actual weather briefing. So most of you probably know that with the 1st of March the meteorological spring has begun, but nonetheless wintry conditions have occurred over great parts of Europe in the last weeks. And here I have some images. For example, here this picture was taken at the International Airport of Frankfurt that was closed for several hours due to heavy snowfall, and the snow clearers were unable to keep up with the work. So the airport had to be closed on March the 12th. Similar picture here from the motorway around Paris, and also there in the northern part of France, in the Netherlands, Belgium, a snow chaos appeared due to heavy snowfall. And only some days later in Hungary, heavy snowfall and briskly winds caused a really dangerous situation where many hundreds of car drivers were snowed in overnight. And you see the winter is really hot this year, and it seems like it doesn't want to stop. And why, or what's the actual weather situation behind all that snow? We will take a look at it now. So I will start with an air mass RGB from March the 11th, 0 UTC. And as you can see, mainly bluish colors on this image. So all over Europe are suffering from these blue colors. And as you possibly know, blue colors in the air mass RGB means polar air masses with a low tropopause. Whereas these green air masses around here in the south of the image are showing tropical air masses with high tropopause. Then we can see these red stripes, for example here or around here. And most of you probably know that these are signs for really dry intrusions where dry stratospheric air, which is ozone rich, is protruding down into the stratosphere and by thus lowering the tropopause. And if you know, on the red channel we have the water vapor difference. This one, I hope you can see it all. Okay, it's not that good to see the water vapor. Brightness temperature difference is on the red gun, and so as the air is really dry, these stripes appear red and can be a sign for PV anomaly and therefore for further cyclogenesis development. And if we compare the air mass RGB with the water vapor image, you can see that these dark stripes really match with the red stripes in the air mass RGB. So whenever you see those red stripes, they can show a PV anomaly, they can show where the jet streaks are, and yeah, you should be warned that there can be some further development. What more do we see? If you just look at the colors, we see this greenish color around here, from Estonia to Russia. I mean, this area down here. I hope everybody can see what I mean. And now I have a question. What do you think these greenish colors can mean? You can use text chat box or raise your hand. And just as a hint, it was mentioned in the first weather briefing this year what these greenish colors mean. So if you listen regularly to our weather briefings, you have a clear advantage. So I'll take a look at the text chat box. Nobody has an idea or is too shy to say it. So I will just zoom in and take a closer look at this section. It is now around here, the green section. It is overlaid with the synop observations, and you see that it's really bloody cold in this area. We have temperatures around -25, -24, and all these low temperatures occur in this greenish stripe. And if we take a closer look at the what's on the green gun in the air mass RGB, I'm typing it down here. I hope you can read it better. Then, so you see on the green gun is the brightness temperature difference between the two infrared channels. The infrared 9.7 is an ozone channel, so you measure the ozone temperature, and the infrared 10.8 measures approximately the surface temperature, and therefore this difference is around 0 or a little bit, or -5, something like that, and therefore the green contribution is really big, and so low surface temperatures appear greenish in the air mass RGB. So you see really wintry conditions, cold in Russia and Estonia. But now we head back to our weather situation. As you see, we are now again on the 11th of March, but now at 18 UTC. We still have, what is of note is this really long stretched air mass boundary. You can see when you look at the colors that there has to be some air mass boundary here. And another distinct feature is this low pressure system here over France. And as I've mentioned in the beginning, there was a snow chaos mainly in France, Belgium, Germany, also in the southern parts of the UK, and now you see why. There are two ingredients for this snow chaos. On the one hand, this really wide air mass boundary here, and the low over here. And as you see, the low is transporting humid air from the Atlantic to the continent. The air is coming from here, so it is really humid, and this humid air mass meets the really cold air over here, and this caused this distinct and heavy snowfall. And I will now try to upshare you a radar loop. I hope it works. So I hope everybody can see it now. Here is a radar loop from this time. You see here the showers developed in the cold air behind the cold front, and here the precipitation originating from the low, and those two air masses meet. And so we also have some convergence effects in the southern parts of the British Isles, and yeah, some heavy snowfall occurred. I hope everybody can see the loop, and I will now wait until it is ready. Here you see really, really heavy precipitation coming from the south, meeting those showers from the northeastern directions, and then some convergence over the, I think it's Sussex, yeah. So back again at the presentation. I hope everybody has seen the loop. Okay. Now I want to continue. I've shown you the ingredients for this really distinct weather situation. And we will take a closer look at the air mass boundary I've talked about, and I will choose this vertical cross-section from the Atlantic to the Mediterranean Sea, the blue one, and we'll take a closer look at this air mass boundary over here. So that's the vertical cross-section. Here are the northern parts, here are the southern parts, and in black you can see the isentrops, and you can see a really strong gradient. We have 300 Kelvin over here and 278 Kelvin over here, so the gradient is 22 degrees, really strong, and it's a really typical cold front. If you can see here, the red lines are the warmer advection, and the blue lines are the cold advection. So we have warm advection in front of and within the frontal band, and cold advection behind the cold front, as you would expect it to be. Another look at the vertical motion at the omega. So you see we have upward motion within and before the front, and some sinking motion behind, again as you would expect it in a cold front. So it's a really regular and really strong cold front, as we can see by the gradient, and it brought really chaotic conditions. You can say we take a look at the meteor alarm. It's a European-wide warning page, and you see the warnings are from the 12th of March, so one day later, and these warnings around here are all referring to snow, and you can see some yellow, orange, and also a red warning. So I think it's the Normandy over here. So the French colleagues even issued a red warning because of the really heavy snowfall, and it was really heavy event, for example, in the region of Somme, the French department Somme, which is, I think, around here. There hasn't been this much snow for the last 40 years, so really snow chaos in the middle of March, when you would expect really spring conditions and not that heavy snowfall. So, and as I mentioned before, that wasn't the end of this air mass boundary. We are now looking at the air mass RGB from the 13th of March 6 UTC, and the air mass boundary still existing and active. It is around here. Oops, doesn't look too good, but you know what I mean. And now I want you to concentrate on this frontal structure down here. What is probably of note in this image before we concentrate on the frontal structure is this this orange spot down here. It's a PV anomaly due to an short trough. Then we have again our really distinct red stripes here because of the jet, which is orientated somewhere here, I think. Yeah, and some nice frontal system over the Atlantic, but I think at this moment no one really cared about, because only some ships are there. But as I've said before, we will concentrate on this frontal structure here and on our air mass boundary over here, our wintry cold front. So now at the same time, 13th of March 6 UTC, I have overlaid the air mass RGB with the equivalent thickness, so we can see the frontal structure with a cold front. I'll take this one with a cold front and a warm front down here. here again our distinct cold front, air mass boundary, whatever you may call it, because there are probably some wave structures in there as well. But you see again the strong gradient in the equivalent thickness, and also nice to see with the help of the equivalent thickness is this system occlusion cold front and warm front somewhere down here. And as I've mentioned before, snow chaos occurred also in Hungary, so you might already know what happened in the future. So we are now 6 hours late. No, it's the same time step, sorry, it's again 6 UTC, and I've just overlaid the mean sea level pressure. You see our low that was somewhere there has now developed in a really distinct low with center over the Mediterranean Sea. And yeah, let's take some steps ahead. We have now the images 12 hours later. You can see our wave structure has developed. It looks really mature now. But what you can also see is this convective cells and this PV anomaly down here, and that marks the position of the upper level low. And if you now overlay it with the mean sea level pressure, you see that the surface low and the upper level low are not at the same position, and that means there is still some development to come. That means that this low is still developing. And also nice if you again analyze the frontal structure. We have here a cold front, then a wave, and something like that, probably with an occlusion down here. And our distinct cold front over here is slowly merging with this system. So you see it over here. What's probably also of note, there are some nice jet fibers over here. But this frontal structure is, I think, is dominating this air mass RGB. So, and now again, I think it's again 12 hours later. You see the system, it looks really, really massive now. It has totally merged with our frontal zone in the north. So I think it would look, if I analyze this, it would look like this somehow. And you can see it's the same effect that occurred in the over the western parts of Europe, that the really moist air from the Mediterranean Sea is transported to the ocean and is mixing with this cold air that is somewhere over here. And this mix brought really dangerous conditions to Hungary. As I've mentioned before, some car drivers were snowed in overnight and nobody could go to them, and they even used tanks to get through, and it was a really dangerous situation. And as you see, there is still some PV anomaly over here, so still some development taking place. And it wasn't only the snow that caused so many problems, but there was also briskly wind, as you can see here. When you look at the gradient, at the pressure gradient, it's really a strong gradient, and that caused really major problems. And for the sake of variety, I've only used, or mainly used, air mass RGB images now. Here is now a dust image for two reasons. The first reason is I want to show you the impressive gradient in the equivalent thickness over here. You have the cold air here, the warm front here, and yeah, that results in a really massive gradient. In the dust RGB, the red clouds or red colors show heavy ice clouds. In black you see cirrus clouds, also green shows cirrus clouds, and low water clouds are more yellowish. There's a second reason why I used the dust RGB here is because it looks like there's some dust stirred up. I mean, I'm no expert in dust RGBs, but I think this is the right color. That should be the sign for some dust in the air. Okay, and now the last image concerning this weather situation is this one. As you can see, it's now 36 hours later. Our system is now really mature with the occlusion over here, cold front over here, and the warm front. And what's really of note in this image, in my opinion, is the post-frontal subsidence after the cold front. Is like if you would draw it with a ruler, it would look like that. So it's really a distinct feature over here. But as you see, Hungary is still suffering from the occlusion, although I think on the 15th of March, the situation was a little bit more relaxed than the days before. And that is the end, not only of the snow chaos at this week, but also of the distinct air mass boundary that brought snow chaos all over Europe. And as you probably might have noticed, snow is the main topic of this weather briefing today, and so I want to continue with this weather situation, but now not again a snowfall event, but to show you how to detect snow cover with the help of satellite images. And it's a little bit tricky if you just have one image and not a loop, because if you have a loop, you see, okay, the snow is that feature that is not moving. But if you just have one image, it can be a little bit tricky. And I will show you how to detect snow cover with the help of some RGB images. I have here the high resolution RGB you see on the red and the green channel is the high resolution visible image, and on the blue one it's the infrared 10.8, so that you can also have some temperature information of the clouds. And as you would probably think of it, snow appears whitish, but there you have the problem, is this now cloud or is it snow? And to distinguish clouds from snow, you can look at surface patterns. If I now zoom in here, probably if you take a look at Poland, you can see, for example, the river Wiesla somewhere here. Okay, now you probably won't see it that good anymore, but you know what I mean. So if you look, for example, at the clouds over here, you don't see any surface features, but if you look at the snow-covered ground, you can see some distinct features down there, and also here seems to be snow. As I've said before, it's a little bit tricky to distinguish snow from cloud cover, but if you look at the mountain ridge over here and compare it to the next RGB that I want to show you, it's the air mass RGB with using the near infrared channel on red, the visible 0.8 on green, and visible 0.6 on blue. You can see that our snow cover now appears cyan, and the formerly white structures over here are also blue now, so it's also snow. And the reason why it appears cyan in this image is because the ice strongly absorbs in the near infrared. So there's no red contribution, and ice as well as ice clouds appear in cyan colors. And here again you have to take a closer look to distinguish ice clouds from the snow cover, and you can also see here the surface features like rivers or things like that. So if you take a look at both the high resolution and the air mass RGB, by distinguishing those, you can see whether it's snow or clouds. And the last RGB I will show you in this connection is the day microphysics RGB. On the red channel there's the visible 0.8, on green the infrared 3.9, but the reflective part and on blue the infrared 10.8. And you see our snow-covered regions are occurring in violet to pink colors. Also here the mountaintops violet to pink. And the main reason for that is that large ice particles diminish reflection in 3.9. So the green channel doesn't make any contribution, and so snow appears pink or violet, whatever you call these beautiful colors. Okay, so we've seen some heavy snow events, we've seen how to detect snow cover with the help of satellite images. And now I want to jump to the actual weather situation and just take a look at it. It's the image from today, 6 UTC, and the situation has improved a little bit. Blue is no longer the most dominating color. We also have some greenish colors in southeastern Europe, first signs of spring there. But in Central and Northern Europe, again, bluish colors appear. And yesterday, for example, in the southern parts and the eastern parts of Austria, again, snowfall occurred. And you can see this really distinctive frontal zone over here. I mean this one. And dry intrusion. Down here you see the PV anomaly, and this PV anomaly in combination with the unstable air stratification caused this really major convective development over here. It looks really, really nice, for me at least. And yeah, if we now take a look where spring is at the moment, I want to overlay this air mass RGB with the geopotential height in 500 hectopascal, and you see all or great parts of Europe are suffering from upper level lows. So I think we have all to wait yet for spring. It looks more like a changeable April weather, or more or less for winter conditions, but a really nice spring bringing high pressure system is nowhere to be seen. So I think spring has to wait. So that would have been my part. So I thank you for your attention, and I would like to give the microphone now to Anna.
Okay, thanks Lily. And hi everyone, it's me Anna Setiawati. I'm forecaster from BMKG Indonesia. So now I'm the PIC responsible for satellite imagery analysis in my institution. Nice to meet you all. This is the first time to me to be an online presenter in wider community in meteorology. Thanks for Liliana and Vesa for this opportunity. My one and only previous experience was to be an online presenter in WMO training, the trainer for RR2 and RR5, which just over around 2 weeks ago. So hi everyone from TNT. And okay, this time I would like to present about the flood in Kudus district area, Central Java province, which caused by extreme rainfall happened in this area. Just to show how we monitor the significant weather in tropical area. So the flood is start from 9 March and until 12 March it's still happening. The extreme weather occur in 9 March at 15 UTC. It's same with 22 local time, and it's amount of 182 millimeter only in one day. So normal rainfall for Kudus is 270 until 336 millimeter for 1 month. So we could say that it is like the total rainfall for 15 days happen just in one day, or 15 times of normal rainfall amount. The water height is reach 30 until 50 centimeters in the village, and around 200 houses submerged. So this disaster affect the agricultural business in the area, especially the rice plantation. So the farmers should harvest the rice of 80 days to get the maximum result. Ideally, it could be harvested after 110 days. It's called the less price up to 70% since its quality decrease. So also the heavy traffic jam around 5 kilometers in Pantura. So let's check how we could find the signature given by the satellite imagery. We could see the convective cloud in here. In over that Kudus area was formed. So we can see the reach of the temperature is minus 63, and from the image, the indirect set, we could identify that the convective cloud was caused by the shear line. You can see there are the shear line and the ITCZ over in northern part of Central Java province. So let's check the satellite imagery. It's still from the MTSAT-RR. So what we could see is when you what we could see, the convective cloud had been growing, started from 9 UTC and reached the maximum grown at 15. And we will check another signature to confirm what we suspect. In your screen, you can see the cloud top temperature evolution. It's star 00 until 23. It's a day because it's every hour. So we can see at the 10 UTC, the temperature measured at 10 Celsius. So, and it increased by the time, and going colder and colder again, and finally reach the top of graphic at minus 633. So you can see, you can see from the 10 until 15, they are colder and colder again, right before it was condensed. So have a look these slides. We could see the water vapor image also from MTSAT satellite. We witnessed the convective cloud here. Convective cloud is very wet condition. So please pay attention to the dark blue color in this. And it was confirmed by the image of the rainfall potential, so as that the rain is in this area, the rain is heavy until very heavy. So it's for the last, we can use the cloud classification. Cloud classification is we use from the GMI algorithm that the color red, you can see from on your slide, that the color is mean CB cloud. So the CB cloud occur around Kudus area. This confirmed by the appearance of the color of the right in radar imagery. Is in the right side, which act as a sign of the value is 60 dBz. So the color is in this 60 dBz, so that the cumulonimbus cloud formation could be confirmed. So this the way we use satellite image for significant weather monitoring in BMKG Indonesia. We check satellite image and confirm the suspect of significant weather with overlay it with wind and sea cloud top temperature evolution, water vapor image cloud classification, and radar reflectivity. Quite challenging, still we have a complex system in tropic, but this make our job interesting. Thank you for your attention. Thanks Lily, Ivan, and Vesa for giving this opportunity to me and BMKG to join the ePort weather briefing. Nice to meet you all. Back to you, Lily.
Okay, thank you very much, Anna, for a really interesting presentation. And I think it was a first teaser for our upcoming next event week, which will be a worldwide weather briefing week. And this will be in the end of May, I think from the 20th to the 24th of May. So just see that you keep updated with our news section, and there you will see everything that is going on. But again, really many thanks to Indonesia. Thank you, Anna. And I think we will hear or see us next time. So goodbye, everybody.